This video will cover the number of significant figures you should display in the result of a calculation when multiplying and dividing. So when you multiply or divide numbers, the result should carry the same number of significant figures. So number of significant figures is the factor, the number that's going into the calculation with the fewest significant figures. In this case, 1.78 would have 1, 2, 3 sig figs. 3.7 times 10 to the negative 5. So this is scientific notation. We'd look at the decimal here. 3.7 should have 2 significant figures. When I get to my answer, the number with the fewest significant figures is 3.7, which has 2. My answer should have 2 significant figures, 6.6 times 10 to the negative 5. So this is a relatively straightforward rule. Let's go ahead and do some practice. Okay, in this first case, I'll take my calculator, I'll type in 0.025, multiply by 4.00. You don't need to type in trailing zeros when you're putting numbers into your calculator. It will drop them anyway. And I get 0.1 in the calculator. The units would be centimeters squared. Centimeters times centimeters is centimeters squared. And I come here, look at the first number, 1, 2 sig figs. Remember, those leading zeros don't count. 1, 2, 3. In this case, the trailing zeros count because there's a decimal point. My answer should have 2 significant figures. The value in the calculator only shows 1, but remember, the calculators will drop trailing zeros, so I need to add that second digit. So 0.10 centimeters squared. Okay, let's go ahead and do this one. So I'll go ahead and type the number in my calculator, 16.4 divided by 32.6, and I'll multiply by 100 to get the percent. The grams will cancel, and I get 50.3067. I'll write down some extras just in case, and it will be a percent now. The times 100% did that. 1, 2, 3 sig figs. 1, 2, 3 sig figs. Now the 100% is interesting. This is an exact value. This is part of the equation for calculating percentage. There's no uncertainty in this number. So even though 100 would have 1 if it were a measurement, this isn't a measurement. And so I have 3 and 3. The smallest is 3, so my answer should have 3 significant figures, 1, 2, 3. I look one digit to the right to round it, 50.3%. Okay, this is an equation. This is the ideal gas law, but I'll recommend, and we'll cover it later, that you write out and do the algebra to rearrange your equation so you get the number you're solving for. Go ahead and write down the rearranged equation. In this case, N equals PV over RT equals, and then go ahead and plug in the numbers. So the pressure here is the 0.994, and then the volume's the 1.413, etc. So we'll go ahead and type this in the calculator. So 0.994 times 1.413 divided by 0.082058. And be careful, even though there's a times there, I'm dividing these numbers I put in already by that as well. So this is going to be, I'm going to hit divide by again, 298.16. You could also put the bottom here in parentheses. I find it easier to just hit divide by the first number, divide by the second, and I get 0.057406. 3 sig figs. This one's 4 sig figs. Now this one's interesting. This is the gas constant, but the gas constant is a measured value. Some constants are not. This constant is a measured value, and I've written down 5 significant figures. There's more on the periodic table handout that you have for exams. 5 is generally good enough, and I'd go look it up if I needed more, but I'll put down 5 sig figs here. And then in the temperature, 1, 2, 3, 4, 5. So the number with the fewest significant figures is the pressure, which has 3. So my answer should have 3. I ignore the leading zeros, 1, 2, 3. Okay, and it gets a little messy to check units, but I end up with 1 over moles, or moles. 0.057, that's a 0 to 4, so the number stays the same. Mole is the answer to this calculation. Okay, so one more, density. So we'll take the 24.621 divided by 1.8. I get 13.6783. 1, 2, 3, 4, 5. 1, 2. The units will be grams per centimeter cubed. 2 is the smallest number of significant figures, so my answer should have 2. That is 6 to 9, so this should become 14 grams per centimeter cubed. Let's do some tricky ones. So in this top one, this includes both multiplication and division, and as long as all of the operations are multiplication or division, we can do it in one problem. So 4.903, I don't need to type in ones when I do this, so I'll skip typing times 1, but I want to divide by that 1.025, and I get 4.7834. The grams cancel, and I'm left with units of milliliters. This number has 4 significant figures. Now, while it's not perhaps immediately obvious, this is a conversion factor. This is a density, 1.025 grams per exactly 1 milliliter. This milliliter is exact, but this has 4 significant figures. And this can be a little difficult to spot, but watch out for that. You'll see this when we do grams per mole or kilojoules per mole or a number of what are called derived units. In this case, this whole thing is one number with 4 significant figures. Okay, 4 and 4, my answer should have 4. So 4.783 milliliters. So that's sort of a first thing to watch out for, is when you have these derived units, these numbers that are per exactly something. Okay, here's another one, 50 pennies. So we'll type in 50, and each penny weighs 2.506 grams. And so I get 125.3 grams out of my calculator. Now this is clearly 4 significant figures, and that's per exactly 1 penny. So this is the same problem we had up here. Okay, a mass per exactly 1 penny had 4 significant figures. This is the interesting one. 50 pennies are discrete values. I can have 1 penny or 2 pennies or 3 pennies. I can't have 0.78 pennies. So this is a discrete value. If I counted 1 to 50 to get 50 pennies, it has no uncertainty, and my answer should have 4 significant figures because this number has 4 significant figures. In contrast, if this were a measured value, 50 would be 1 significant figure because the trailing 0 isn't significant without a decimal point. So the context of this being pennies tells me this is exact, and therefore I'm looking at 4 significant figures in my answer. Okay, in this case, we'll get 0.04186. The milliliters cancel, and we're left in units of liters. This number has 4 significant figures. This is a definition. This is the definition of the milli prefix of the SI numbers. This is exact. There is no uncertainty. It's exactly 1,000 milliliters is equal to exactly 1 liter. And so when I do this calculation, my answer should stay at those 4 significant figures. So in general, we're just going to count all the numbers that go into it. Watch out for the derived units. Watch out for discrete values like numbers of shoes. And watch out for defined unit conversions. Go ahead and pause your video and answer this question. Okay, so up here, 3 sig figs. I don't count the leading zeros. This is scientific notation, so I look at the decimal part, this part here, and this is 4 significant figures. In this last number, there's no decimal point, so the trailing numbers don't count. This is 2 significant figures. So my answer should go to 2 significant figures. I look one to the right, it's 5 or above, so I'm going to increase this number by 1 and I get 0.31. The answer should be B.